Okay, what I would like to do, today's lecture will be on dictionaries, data structures, which is the mother of all data structures as far as I'm concerned. And just to remind us, before we get into this thing, exactly what are the operations that need to be supported by dictionaries. And the rules are that there is a search procedure. Do you guys see my mouse when I'm wandering around the screen?
Yes.
Hearing some evidence of yes. Okay, and by the way, some of you guys turn on your cameras if you can, just so I know that there's live people out there. But search asks me I'm given a dictionary and I am given a key. And my goal is to find a pointer inside the data structure to the record that is associated with that key, or a nil pointer if it's not. There's no. The key is not in the dictionary. Insert says I'm given a pointer to an element outside the data structure, so it's got a key field that may have some data baggage. Okay, and I want to insert that into the dictionary. Delete, I'm given a pointer to the element in the dictionary, and I want to then get rid of that element, remove that element from the dictionary. And notice that I'm asking for a pointer here. There's a difference between, this is so that I don't have to do a search operation if I have the pointer. If I just have a key and say delete the record associated with Skeena, you look up the pointer to Skeena, that's a search, and then you then you delete now that you have the pointer. But if you have the pointer, it might be more efficient because you won't have to pay the cost of the search. Any questions?
Just to clarify, the pointer, when it says X, does that mean that it's a pointer to X or just the element X and we have to find it?
That is a pointer to the element X. Okay. We're assuming that it's a pointer to the element X, and there's nothing to find. We have it. Pointer, I have the finger right on it. Okay? And search, we have a key. We don't know where it is. That's why we get a pointer from a search. Okay? The other operations that are important are minimum and maximum. Return the largest and smallest element. Okay? And notice in red the logical predecessor and successor. If I am pointing to an element, I want to know what's the element. The predecessor is the one that appears before it in sorted order. The successor is the one that appears after it in sorted order. Okay? What is the value of predecessor and successor operations? Can anybody figure out why I want these kind of procedures? What can I do with it once I got a predecessor and a successor?
Sorting.
Sorting, I could start from the beginning and I can cruise through and repeatedly say, give me the successor. Start with the first element and say successor, 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 and it will pull them out in sorted order. Okay, so it's a useful way to walk through the elements in the data structure. Any questions? Okay, now what is the problem of the day? Problem of the day says I want to now know, and I want an implementation of those 7 dictionary operations. I don't know if it was 7 or 6, something like that, number of dictionary operations. But I want to use as my underlying data structure either a doubly linked or singly linked list that's kept unsorted, or one singly or doubly linked that are sorted. So there are 4 different implementations, 7 different operations. It does look like 7. Okay. What is the running time of me doing this? Okay. I want to now know the big O complexity of all these operations on those underlying data structures. And the way to do this, the important thing to do here is to understand that I have an implementation before my eyes. Okay? that I have written down on, either on a sheet of paper or on somewhere on my retina, what the implementation of these things are. So it's important that the analysis is of a piece of code that presumably exists, okay? And we're not just randomly shouting out complexity classes here, but we have to see how we're implementing them, okay? So singly linked unsorted lists. Somebody who's going to volunteer me. How fast can we search for a particular key on that? I'm going to go down the first column. What's the right way to do that? Somebody.
Wouldn't it be O of N?
O of N, how are you going to do it in O of N?
Search every element.
Just keep bopping through a list while it's not nil. Are you the guy? Fine. Insert. How much time is it going to take for me to insert this thing into my data structure?
O of N again.
Okay, O of N would mean that you're saying to me, I've got to go through all the elements, pop, 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 to then figure out where to insert it.
Yeah.
Okay? I can take advantage of the fact that this is an unsorted array. How do I go and insert it into my data structure? I claim that I can do it faster. How would I do it faster?
Make the new one the head.
Add it to the head, right. So I've got something where I've got L is pointing to some kind of list. If X is pointing to somebody new, what am I going to do? I'm going to say X.next is equal to L, and then L is equal to X. Okay, and now it's in there, and that took constant time. Boom. What about delete? Now I've got an element X that is pointing somewhere in my linked list. How much time does it take to delete it, given the pointer here? I'm seeing N. Why is I seeing one person confessing to constant time? Why does someone think they can do this in constant time?
You can swap it with the head and then just delete the head.
Okay, so now what you're saying here is I could swap it with the head and delete the head. Okay, so let's think about this for a second, because this is why we need to be careful. The first problem is, of course, it's a singly linked list. So I don't have the ability to, identify who is the guy that points to me. It's one of these conga lines. I don't know who's on my back, right? So there are different ways to do it. The more obvious way to do it would take order N, find which element points to me, and then reroute that pointer. That would be my obvious way of doing it, okay? So that would be the obvious way, but that would be order N. Now there's a question of, is there a way I could do this better? And here it becomes a little bit tricky. And it's not immediately obvious to me how I'm going to do this, okay? There may be ways of doing it by manipulating the pointers, but this is one of the dangers of having a singly linked list, okay? I've got to change this pointer on some level if I can, okay? Any questions? That was going to be the delete. So the delete to me looks like, if I didn't know better, at least for now, I know how to do it in order N, but I'm not sure I know a better way to do it. What about predecessor? How much time does it take to find the predecessor? Okay, I'm seeing various ways of spelling N. And why is that? It's because I want to, I'm going to go through all the elements of my list and say, are you smaller than I say X points to it. I've got a min. Are you smaller than what X points to? And are you bigger than the smallest thing that we found so far that X points to? So that would tell me that this is an order N thing. And presumably the same thing, is the same thing true for successor? I think that's true for successor. Okay. How much time does it take to find the minimum or maximum element? I'm hearing people say order n. Is there any way I could do this more efficiently, however? Okay. By maybe keeping, if it was sorted, maybe. What if, let's say, another way I might have done it, what if I keep an extra pointer, and I'm going to call this one min, and I'm going to call this one max, and I have this point to the minimum and maximum element in the data set. Okay? Could that be something that I would be able to do? If I have these pointers, how long would that take for me to find the min or the max? Constant. Now, what do I have to do in order to have these pointers? I've got to maintain them, right? What operations do I have to change if I'm going to have these min and max pointers? Every time I insert an element, how would I change this on an insert? What do I got to do on an insert? Again, I like when people talk to me, not just type to me. What would I have to change the insert in order to use these pointers?
Check if it's a min or max.
What?
Check if it's a min or max.
Okay, I'm going to check if if the new item that I'm inserting is bigger than the min, I don't do anything. If it's less than the min, I'm going to change the pointer to it, right? So on an insert, that would be a constant extra amount of time. How would I have to update these pointers if I do a deletion, however? How much does it cost to update the minimum? If I want to update the pointer to the min, what do I have to do when I do a deletion of an item?
Wouldn't you have to go through the whole list and check which is the next minimum?
If I delete the element I'm deleting is the min, then you're darn right, I have to go search for it. How much time would that take?
O of n.
O of n. How much time is my deletion currently taking? O of n. How much is n plus n? N. Okay, does everybody see that I could spend an extra, if I spent an extra order n time on every insertion or deletion, and every deletion, that wouldn't change the complexity, right? So if I am clever, I can keep my pointers to these two. It's only a constant amount extra space in my data structure, right? And the work I do on an insertion is still going to be constant, and the work I'm going to do on a deletion is still going to be order n, right? So does everybody see how I could get these? Any questions? One of the key things about building a data structure is you can't analyze the operations independently. Sometimes you need work done here that you're going to exploit over here. And that is what we're doing in this case. Any questions about that? So I think I can implement these operations this fast, and that's a good thing, okay? Now, what about a singly linked sorted list? How much time will it take to search for a particular key in a singly linked sorted list?
Log n.
Okay, I'm seeing log n with binary. If I'm using a linked list, how do I go use that in a binary, in a linked list? I need to grab the middle element. That's what worked great about binary search in an array. But how do I grab, what do I have to do to find the middle element in a linked list? I've got to bop over n over 2 items. Does everybody kind of see that? Does it being sorted help me at all with a with search? I don't believe it does. In the worst case, if I'm searching, the element is at the end, you're searching for ZZ top, okay? He's not going to be till the end of the thing, right? So as far as I can tell, that is an order n operation, okay? Any questions about that? Arrays give me constant time access, linked lists don't. And that hurts me here, right? Does everybody see that? Okay. How much time does it take to insert somebody into a singly linked sorted list? Okay. Suppose I even know where it's going to be. Okay. Insert means that, well, actually, I guess I got to find it. I've got an X pointer to my element. I don't know where it is. I have to find where it goes. That had better be order n too. Okay. What about delete? What if I am given an element to delete? I've got a sorted list here, and I've got an element to delete. What do I have to do? Okay, I want the predecessor. Okay, unless I do some magic. Okay, then it looks like that's still going to take order n. Is that right? How much time will it take to find the successor of an item? Successor is constant time, right? That's the guy right after me on the linked list. If you have a pointer to me, my next guy dot next is my successor. So that's good. I can do that one quickly, right? How much time to take to find my predecessor? Seeing order n, again, I want to get back at this guy, can't do it, okay? So I think this one is order n. What about minimum and maximum? Okay. Well, now presumably I'm still spending order n on an insertion and on a deletion. Every time, you know, on a deletion, I can find the min and the max. Well, okay, wait. So I'm still spending the time on an insertion. So long as I can maintain pointers to the min and the max, I think I can do the exact same thing I did before. Does everybody agree with that? And I'm going to say the answer is yes. This should be order one, order one. The min pointer, assuming it's sorted in an increasing order, then the min is simply what's pointed to by the head. I need a tail pointer for the max now. Any questions about it?
I have a quick question.
Yeah.
About the successor and predecessor operations for sorted lists.
Yeah.
So it makes sense to me, but I remember looking at the slide definitions for successor and predecessor, and it says that X is an element, not a pointer, whereas like the definition for delete says that X is a pointer. So I don't know if I was
No,
misunderstanding.
so X is a pointer to the thing. You're asking for the successor to an element that you are pointing to. So you're given a pointer to the item. You don't have to start by doing a search.
In successor and predecessor, X is a
Yes,
pointer.
successor and predecessor and delete, I've got the pointer to it.
Okay, cool.
Insert, I've got the pointer to my element, but it's outside the data structure. That means I still have to do whatever I need to do in the data structure to find where it goes.
Got it. Thank you.
Okay, fair enough. Now, how does this change with a doubly linked unsorted list? Okay, search, I claim, is still going to be order n. What of these operations might get better with a sorted list, with an unsorted but doubly linked list? Which operation can I hope to get better? Okay. Okay. I'm seeing deletion and predecessor. Predecessor, right. I can go back now. I can now reach to this guy. And once I reach to the guy that's behind me, that's good. And that's also true for deletion. So there is a vision that in an unsorted way, I could insert it in constant time at the front. Well, actually, let's just think about this a little carefully. If it's unsorted, I can insert it in constant time. If I have a pointer to it, if it's doubly linked list, I should be able to delete it in constant time. That's good. Successor, okay. How much time will it take to find my logical successor? Well, if it's unsorted, I've got to cruise through all the elements. This had better be order n, right? How much time to find my predecessor? I've got to go through all the elements. This is going to be order n. To find the minimum, well, if I keep track of the minimum and the maximum, maybe that's good, but let's be a little bit careful here. If insert and delete, what am I going to do on a delete? Can I maintain my minimum and maximum pointers quickly? I'm going to claim I don't see how to do it, right? If I delete the minimum, where is the next minimum? It looks like I got to go through and do a successor, right? So in this case, I don't really see a way to do that fast. I think I'm going to make that O of n and O of n. Does everybody kind of see that? Because I can't, before I could hide the cost of maintaining the pointers in the insert or delete, but now it's too expensive. Okay? Insert's not the problem, delete is the problem. Okay, what about a doubly linked sorted list? Okay, now how much time does it take to search in the doubly linked unsorted list? How much? Okay, I'm hearing log n, but I don't know how am I getting to the middle. I don't know how to get to the middle. If I can't get to the middle, it doesn't do me any good that it's sorted. Okay. Insert and delete. How much time does it take to insert something into the doubly linked unsorted list? Okay. I am going to claim I got to find where it goes. That's still going to be order n, right? How much time does it take to delete a guy in the list if it's sorted, if it's doubly linked? Well, now I can just patch, splice me out of the list, right? I can find the guy behind me. I can find the guy ahead of me. Delete me, it's still sorted. That's constant time. How much time does it take to find my successor if it's a doubly linked sorted list? Constant time. And how much to find my predecessor? Just a guy who's got the hands on my shoulders. That's constant, right? How much time would it take to find the minimum? Well, the minimum's always on the head, so that's there. And if you believe I keep a tail pointer, I can now maintain the tail pointer when I get deleted. It's my predecessor. So this I can do comfortably. Does everybody see now kind of where I'm coming from? Okay. This is the kind of reasoning you want to do when it comes to building data structures. There's a bunch of operations. You want to figure out where can you do the work that is necessary to make it happen in order to run with the complexity that you think you want it to. Any questions about these?
Hey, Professor.
You
You can go first.
Oh, sorry, my bad. Can you go back to why for the doubly unsorted minimum and maximum, you can't just do the same thing you did for singly unsorted? The doubly unsorted.
What is the problem here? Okay. The idea here is I'm going to keep a pointer to my minimum and maximum element, right? Now, suppose that I delete the maximum element. I've got to find the next maximum element, right? And if so, that becomes a problem. Now there's an interesting idea here on the board, which is I could keep a stack of minimums and maximums. And the claim here is that you're telling me that I'm gonna keep a stack of all the minimums so far, right? Insert the smallest minimum. If I get another one, the old one is still there. Does everybody see what his idea is? He wants to keep a stack and keep all the minimums so far. So originally the first element is here. The second element will be here if it is less than the first element, maybe -5. if we insert somebody less than -5, let's say -7, okay, that'll be here. Now the claim is if I delete -7, the top of the stack will have the min. Does everybody agree with that? You shouldn't. There's a little problem here. What is the problem?
I think if you like did something like you inserted 7 and then you inserted 3 and then you inserted 5, so it's 7's your original minimum, then 3 is the original minimum, and then you put in 5, which is between those two. So when you would get rid of
Now when I
3,
delete 7, 3, it's not there, right? So if I delete 3 now, 5, which was the minimum before this, okay, isn't never was a minimum until I deleted 3. Okay, so that's going to break the stack idea. Or if I happen to delete elements that are on the stack, okay, in the middle of the stack, it will be expensive for me to go over it. But I think I like that as a more fatal problem. Okay, any questions about that? Okay. What other questions? Somebody else with it. And so now there's a question of how can it be constant for singly linked but not doubly linked? Okay. And the reason here is that in my current drawing, I am spending order n time on an insert and a delete. I can use whenever I do an insert or a delete, I could cruise through all the elements to find the new min or max. Okay? And so I'm going to pay for the cost of updating my pointers to the min and the max. In the order n time, I have to do an insert or a delete. If I want to do my deletions quickly, okay, insertions and deletions quickly, I can't do my min and my max quickly. Okay? Any questions about that? I could have done this in order n and this in order n and then do these in order 1. Okay? But I like the fact that I can now do insert and delete in constant time. Okay? Maybe that's interesting. Okay? Any questions?
Professor?
Yes.
Yeah, I was just gonna say, since the question asked for the worst case, would we put on a test just like O of n for singly unsorted, even though we could have O of 1?
Okay, didn't say that again. I didn't hear it.
Since the daily problem asked for the worst case running time, would we put O of n for the minimum and maximum for singly unsorted?
Would I say for singly unsorted, is the worst case time going to be order n? The answer is no, not if you implement it right. Okay? I'm always going to have a pointer from the min and the max element. And I'm going to do an extra order n work on my insertions and deletions to make sure my pointers are always correct after an insertion or a deletion. Right?
Yeah.
If I maintain these pointers properly, this is always going to be order n, order constant time. Okay?
Okay, I get that. Thank you.
Okay. So what is the important point here? It should be clear that how I implement that, I have some freedom to operate certain operations fast at the cost of making other operations slower. Okay? I've got, I've got choices I can make. I've got different options, but I can't make them all fast. Okay? Sometimes there are, there are trade-offs. Okay? And that tells me that if I want a data structure where I'm going to be doing a lot of inserting and deleting, but not a lot of minimum and minning and maxing, then I am better off using the doubly linked unsorted list. If, on the other hand, I'm going to insert and delete a lot of things, but ask a tremendous number of min and max questions. Okay, maybe I'm better off with this flavor. Any questions about what these trade-offs are? Okay, any more questions? I'm not going to read any more complicated questions now.
Professor, so what if we use a theta of n and theta of 1 instead of O of n? What does that difference make?
Something that you might say is, my big O, I tend to be maybe sloppier than I should be. Big O means I described ways of doing these. Okay? In fact, I will claim all of these big O's are thetas, if so long as I give you a the worst case example, it really takes that time. Will searching actually sometimes take order n? Actually take n steps, omega n steps? Yeah, if it's at the bottom. Okay, if it's the last element on the list. Constant time, well, as long as I do one step, it's constant time. So that's in fact pretty much gives me a theta for free. Delete, well, if the element I'm deleting is the last element on the list and I got to find it, that's theta n. Do you see that there's a simple argument with all of these, presumably, that says that in fact the worst case can occur. Okay, that I haven't been sloppy in my analysis here. The programs that I'm taking really actually do take this much time. Okay? Any questions? There's some questions this way to say, are you cheating by having these extra 1 or 2 pointers? Adding a constant amount of memory to my data structure. Okay? And so that I can do these queries faster, that's perfectly fair game. Okay? So long, but if I have these pointers, I got to pay the cost of maintaining it. And that's what we're doing up here. Any questions? Okay, any questions about that? I encourage you to think about this thing, but to realize that what data structures means is that there's a mix of operations. And sometimes I pay for part of one with some of the costs of the other. Any questions? Bingo. Okay, so now that we understand how to implement dictionaries by linked lists and by arrays, we did arrays at the end of last class, what would be the classiest way, in a worst case sense, to implement all these operations is a balanced binary search tree. And so let's talk about binary search trees here. A binary search tree is a data structure that lets you support all of these dictionary operations effectively. And what is it? Well, basically every item is going to be a node. There is going to be a key field. Okay, that's going to be the key of the element. Maybe there's some data fields if I want data fields. But the important thing, there's going to be a left child and a right child. Okay? And these are going to point to my left child or a right child. So again, a binary tree is a rooted tree where every node contains at most 2 children. And every child knows it's either a left child or a right child. Just like all of you are children of some family, okay, node. And you know whether you are the first child or the second child. Okay? Any questions about that? A binary search tree is a binary tree that has the property that it is a label, okay? That every node is labeled with a key such that for every node, all the keys that are of its left descendant, for any key, any node in a binary search tree, okay, all the nodes that are on the left subtree are less than it. So if this node 7 has a key of node 7, all the nodes to the left are less than it, and all the descendants in its right subtree are greater than it. That's what a binary search tree is, if we have that property. If you look at 2, what are all the keys in this data structure that are less than 2? Well, there are none of them. And why do we know that? Because if so, they would have to be in the left subtree. Any questions about what a binary search tree is? It's a binary tree where the labelings, the keys, with a key associated with each node, such that it has this binary ordering property. Okay? And the interesting thing is, for any topology of a binary search tree, there is only one way to label the nodes such that it has that property. Okay? Let's say that I wanted to relabel this tree where my keys were letters A, B, C, D, E. Actually, how many do I need here? I think I need more than E. I think I need an F. Okay? What do I know about this search tree? Where does the A node have to be? If I'm going to keep this shape, where does the A node have to be? A is less than every key, right? If it was, it would have to be kind of on the left subtree of the root. If that subtree doesn't exist, it's got to be. This is where A would have to be. This, I claim, is where B would have to be. Well, what's this? B is going to have to be greater than an element greater than A, but less than everything on its right side. Yeah. What about this? We know that in this subtree, any element, the minimum element on this subtree had better be on the left side. So this is where C is. This is where D is. This is where E is. And this is where F is. The interesting thing is that any binary tree structure has exactly one labeling with any given set of keys for it to be a binary search tree. This is important because the labeling is what has to be in the right order so we know where to find things. Okay, any questions about that? Any questions about that binary tree, search tree? The structure of it when you're implementing it is basically what I said, that you're going to have a, it looks like here I have a data item, which I guess is going to be my key. Arguably, I could have a data item and a key. But it looks like in this implementation, I have my key, I have a pointer to the left child and a pointer to the right child. And in this one, it looks like I got fancy. I had a pointer to the parent node. Every element has one parent in the binary search tree. Which element in the tree doesn't have a parent?
The root.
The root, okay? So except for the root, it doesn't have a parent. The parent of the root would be nil or null, okay? So I could explicitly maintain the parent. Usually that's not really necessary. But if I want a parent pointer, I could have it. And it would give me constant time pointer to my parent. I can have this pointer so long as I update it in any operation that changes the tree. That would be an insertion and a deletion. Okay? Any questions? You can have it if you can maintain it. How do I search in a binary search tree? Well, if I'm given a pointer to the tree and I have an item that I care about, if the item that I want to insert, okay, is what my root pointer points to, then bingo, I have the element and I can return the root pointer. If the root is null, okay, then that means that if I do something like L points to item, I'm going to get a crash. So I better check first, is the item going to be null? If it is, return the null pointer. Okay, if not, then compare the root to my key. Is it what I want? If so, return it. If not, compare it to the children. If X is less than what the root points to, then is less than the root value, the item's going to have to be on the left side of the tree. Otherwise, it'll be on the right side of the tree. Any questions? What is the time complexity of searching in a binary search tree?
O of log n.
Okay, I'm hearing O of log n. That's true if the tree is of height log n. Okay, unless I am doing something to maintain that tree of height log n, I don't know how I can make that claim. Okay, you're telling me the worst case is order n. If I do nothing, if I have n nodes in the tree, the worst case is going to be if I have a twig. Okay, so yeah, it could be, you're right when you say it's O of n. I would prefer to say it's O of h, where h is what the height of the tree happens to be. Okay, and that way it's true for the guy that if the height is order log n for some reason, it's going to be log n. The height is going to be order n. But why is it that? If you think about it, it's because I am going to do constant work. O of 1 work here. O of 1 work here. Doing this thing, it's going to be another O of 1 work. And then I'm going to have a recursive call on something 1 node down. I've spent constant amount of time while lowering the height of the tree that I care about by 1, right? If I wanted to write this recursively, I could say that the height time to search for a tree of height h would be the time tree of height h minus 1 plus constant. And this is going to be, if you figure that out, that should be O of h. I'm doing constant amount of work per level, and I'm going to go down at most h levels till I'm done. Any questions why this is an O of h operation, where h is the height of the tree? Or is that believed? Any questions? Bingo. And this is basically what that argument is. What's great thing about a binary search tree is that it's a recursive structure. If you delete the root of a binary search tree, you get 2 binary search trees. Okay? If you delete the leaf of a binary search tree, you get 1 binary search tree, a smaller one with 1 less node. This is a recursive kind of an idea. Any questions here? Again, a recursive object is what you call it, something that, when you take something out, you get a smaller instance of it. One of the readers of my book recently sent me in an argument. They said that a salad is a recursive object. Why? If you take a bite out of a salad, what do you get? You get a smaller salad. Whenever you eat a piece of lettuce, what's left? It's a smaller salad. What happens if you delete all the tomatoes from a salad? It's a smaller salad, right? Is a hamburger a recursive object? What do you get when you eat a bite out of a hamburger? You get something disgusting, right? It's not a smaller object. So kind of thinking about it, a salad is kind of a recursive object in a way a hamburger isn't. Okay, any questions about that? Okay, and likewise, binary search trees are recursive objects because you can remove a part of it and you still get a binary search tree. B. Any questions about that? Okay, so what about operations? We've shown how to search a binary search tree in order height time. How do we find the minimum and the maximum element in a binary search tree? I want to claim that if I have a binary search tree and I'm starting at the root, the minimum element has to be smaller than the root. Okay, it will be smaller than the root on the left side. It's got to be on the left side. Unless the left, if the root has a non-nil left child, then the minimum element has to be on the left side. If it's nil, it means that now then it means the root is the min. My claim is that in constant time, I can test, do I have a non-nil left child? If so, recur to the next level. My claim is by bopping down left pointers in a constant time per element, I will get down there in what time? How much time will it take till I find? The min is going to be if I keep following the left children till there's no left child. How much time is that going to take? Somebody? O of H. Does everybody see that the same thing is true, except that now going down right children will lead me to the max? Okay? So my claim is that both min and max I can find in time proportional to the height of the tree. Any questions about that? Okay, that's good. And again, this is a recursive implementation. It is not a recursive, this one's an iterative implementation, it looks like. Basically, I'm going to, again, spend constant time to make sure it's not null now. So long as the left child is not nil, bop down to the pointer. This is going to do constant time. This is going to take, it's constant per level. And then I'm down to a lower level. The time is going to be the number of levels or order H. Any questions? Right. Now, predecessor is a little bit of a trickier operation here. And this one requires a little bit of thinking. Where is the guy before X in sorted order? Okay. And let's try to think with a search tree. It should be clear that as we work down a search tree, the deeper down we go in the search tree, the range of keys that we are possibly considering is getting narrower and narrower. In the beginning, before I compare to the root, and I say, where is this? If I want to look for a particular node, the element could be any one of the nodes. Once I go down one level, these are all the nodes that are less than the root, right? If I go down this node, these are all the nodes that are less than the root, but greater than X, right? If X is an internal node, where is its successor going to be? It's going to have to be greater than X, so it's got to be on this side. And it's got to be the smallest such thing. So it's got to be the min of that subtree. Does everybody kind of see that? So if an element is in the middle of my search tree, okay, what is the successor of X going to be? Well, it's going to be on the min of the right child, meaning I go to the right child and keep going down left pointers, right? So if that's true, it took order H time to find the min. It would take a constant time to go down, right one level to find the left child. That would, or right child, depending if I want a predecessor or successor. I claim it's going to be constant time plus the cost of a min or a max. If I have my element in the middle of the tree, it's going to be done in order H. Any questions about that? That's one you may have to figure out a little bit when you think about it. But what is the predecessor of an element that does not have a left child? Right? If you look at this particular example here, it does not have a left child. So what would be where would its predecessor be? okay, it's got to be earlier in the tree, okay? And if I keep walking up, left children, my left child here, okay, if I have a left parent, I'm less than my parent. So that can't be, my parent can't be my predecessor. This guy is less than my parent, okay? My grandparent is less than my parent. Oh wait, let me make sure I get this thing right. If we compare me to my parent, okay, my parent is going to be bigger than me, right? Because I'm on the left side of my parent, I'm less than my parent. I'm less than my grandparent. I'm less than my great-grandparent. The node that is right before, that is less than me by the smallest amount, is the first right child of an ancestor. Does everybody kind of see that? My predecessor could not have been these guys. It's got to be the first right child, okay? The first pointer that has a right child among my ancestors, okay? So if I have a parent pointer maintained it for myself, I can keep walking up my parent. Are you my parent? I can walk up to my parent and then say, am I a left or a right child? Okay? By comparing whether the pointer to me is this or this. I can keep walking up until I find a right child, and that one is the predecessor. A different idea is going to be with successor. Suppose I want to find the successor of a particular node. Okay? If I keep having this a situation where I'm a right child, I'm bigger than my parent, I'm bigger than my grandparent, I'm bigger than my great-grandparent. Until I get a left child, that's going to be the one that my successor points to. Any questions about that? Do people kind of see how that works? Do you see that if I have a parent pointer, I can walk up the tree in height, time, constant time per level, and then check to see whether I am my parent's left or right child, okay, in constant time. So what is the time it takes to find a successor if I'm a leaf node? What is the worst case time it might take? Okay, starting to see people, I like to hear people shout it out, order H, right? Which node does not have a successor? Is there any node that does not have a successor?
The maximum?
The maximum element, right? Who's bigger than the max? Nobody bigger than the max, right? And how do we know that? Well, what's going to happen? If I want to find my successor, if I'm the max, I was already a rightmost child, right? Bop, 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 never got a left, right? So my claim is that the max does not have a successor and the min does not have a predecessor. And I can find all this out in time proportional to the height of the tree. Any questions about that? Does that kind of make sense? Boom. Now, one operation that isn't a dictionary operation, but is a phenomenally useful operation on trees, is the idea of an in-order traversal. Did you guys study in-order traversals in your data structures class? Is this, other people mention this?
Yeah.
Okay, so there, yeah. What is an in-order traversal? It is a search procedure, a recursive search procedure. Note that traverse tree is calling traverse tree, and traverse tree. So there's some recursion going on. And it says that basically, so long as my tree L is not null, visit everything on the left, then print the item, print or process the item on the root, and then do everything on the right. In a binary search tree, this will process everything in sorted order. Why is that? Because when I process my item here, what do I know? If it's in sorted order, all the elements less than it had better have been done. All the elements less than me as the root are the guys on my left subtree. Does everybody agree? So this will produce things in sorted order once you have a binary search tree. Now here is the $10 question. Oh, okay, hopefully this will, look at that, isn't that power? I can make that go. Okay. What is the running time of tree traversal? This is I want people to think about it. What is the running time of tree traversal? Okay. I'm seeing order n. Why is it order n? Can anyone give me an argument that this is an order n operation? It says visits all nodes. I said, well, it visits all nodes, but it's also a question of how much work does it do for every node? Does everybody agree? Look at this code, okay? It is doing a constant amount of time per operation, per call. Actually, let me go and deal with that, right? The processing the item is assumed to be 1 constant time. The doing the if is constant time per work, per node. Then it recurs to the left, it recurs to the right. But for every node, it's going to be doing a constant amount of work. That is why it is order n. Okay? If you want to think of it recursively, one way to think about it is that, no, I think the way I like to think about it is that argument. I think that's the argument I'm happy with now. Okay? There are a total of n nodes in the tree. It's going to do it's going to process each item exactly once. The time it takes is the time it takes to process the item, plus the associated other constant effort per that call. Okay? The time is going to be order n total. N times a constant, O of n. Any questions about that? So being able to do an in-order traversal is a good thing. Some people are saying, well, is it order H? And the answer is no. If I have a nice fat tree, a nice tree like this, suppose it's perfectly balanced. It's got n nodes. What is the height of the tree going to be if I have n nodes? If it's perfectly balanced, what's the height of the tree going to be? Not hearing it. I'm seeing people type. People don't seem to speak anymore. I hear log n. Now, you've got it to do a traversal. It's got to visit every node in the tree, right? What's going to happen on the traversal? Bop, bop, bop. Okay. Actually, let's say do that one. Print it out. Come back here. Print it out. Go to the right side. Do the bop, print it out, back, print it out, go to this side, done, print it out, up here, print it out, go to the right, print it out, bop, 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 print it out, go to the right, go to the left, print it out, come back here, print it out, go to the right, print it out. Does everybody see what's kind of happening on this? The time it's taking is, no, not that. Do this, do that. Bop, bop, bop. Okay? I'm spending constant time per element, and this will be doing it. Any questions? Okay. Any questions? Okay. Good. So the other operations that happen on a binary search tree are insertion and deletion. Okay. And how do I insert and delete a new item into a binary search tree? Well, I have to insert it where I can find it. If I want to insert an item, okay, let's say this was 5. Let's say I'm inserting an item 17 in the tree. Okay, if I insert it over here, it's on the left subtree, it's got to be less than 5. This item can't possibly be 17, right? So that's a wrong thing. But suppose, let's say that there is an item, item 3 in the tree. Maybe I want to insert an item 3. Okay, it's got to be on the left side of what the root is. If the root is 5, it's got to be on the left side. If the value here is 2, okay, then it's got to be greater than 2. It's got to be on this side. If this guy was a 4, then it's got to be on the left side. My claim is that to insert something into a binary search tree, I've got to insert it where I'm going to be finding it. And in order to do that, my only choice is basically put it at the leaf level to replace a nil node with another node. Okay, and the time that's going to take is constant time per level till I find the nil pointer I want to replace, and then replacing that nil pointer with the one that I want. This will be constant times the height of the tree. This is going to be order H. Any questions on the insert?
Professor?
Yes.
So we said earlier that the min and max operations were O of H. If we accounted for like the min and max as pointers while inserting and deleting, can we also make that O of 1?
Okay, so you're saying, could I do the same trick where I I keep pointers to them so I don't have to go down there? The answer is, if I can find the predecessor, okay. So the real question is, the only time the min will change is if I insert a smaller value or delete the min, right? I've got to find the successor in a certain amount of time. If I could find the successor in constant time, I could keep a pointer to it, right, to the min, and I could update that. Or if I could update the min pointer, if time proportional to the height, when I did the insertion. Let me just take a look at that. Say one more time. If I did a deletion of the min, I could find the new successor in time proportional to the height. I could keep a pointer to the min, right? If I insert somebody less, I change my pointer to it. If I delete the min, I do a search. So long as I'm spending order H time for doing insertion and deletion, I could afford the time to do a successor or a predecessor if I delete or insert the new min or max. So the answer is yes, I could arrange to do min and max in constant time while keeping all the other operations order H.
Okay.
It's a long way of saying it, but I think everybody agrees with that now. Any questions? Okay, it's a question of whether I have time to maintain my pointers. And this is what the insertion looks like. I'm not gonna, you should look at it just to make sure you know how these things work. But basically, I'm recursively finding the right spot by going to the left or right like it's a search. And then this is the thing, once I found that nil, create a node for my key and stick it there. Any questions? The final operation on a tree deletion is here, okay? And what is my situation? Deletion turns out to be trickier than insertion, because it's the element I'm deleting is not necessarily a leaf. Okay, so there turn out to be a couple of different cases of deletion. Suppose I delete the element 3. Okay, you tell me delete this guy. Can I find its parent and zero it out and no one will know or care that I was ever there? I claim the answer is yes. So deleting a leaf node is an easy case. So long as I can find the parent in constant time, which is why I got a parent pointer, that one's easy. This could be done in actually constant time then, right? Or, yes. Now, what if I delete a node, okay, that, that has one child but not the other child, okay? Suppose I now try to delete node 6. Note that it's got one child after I'm left. So I only need to find room for one pointer to connect its descendant to the tree. I've got one pointer that was pointing to me before, okay? The interesting thing we know is everything that on the right subtree of a node has got to be greater than it. If I delete this guy and wire this guy directly to me, everything on this right side of me is still going to be greater than me. I still have a binary search tree. Does everybody see that, in fact, it's not the second case, that if I delete a guy with one child, it doesn't matter whether it's a left child or a right child, I have one spare pointer, okay, created, one spare parent pointer created by my demise, and I can simply plug in the descendant and have what used to be my parent point to my descendant. Any questions? That is the second case of deletion. The harder case, the one that's really the challenging thing, is what if I want to delete a guy that is has two nodes? Let's say I want to delete item number 4. Okay. If I pull this guy out, both of these, my children, want to be connected to the tree. The parent of me has only one pointer to give. Does everybody see what the problem is? Okay, how do I solve this problem? There's a little bit of a clever way of doing it. What if I relabel myself with my descendant? Okay, so my successor. If I am an internal node, where is my successor? My successor is going to have to be to the right, the leftmost descendant, right? I could overwrite myself with the node of my descendant. And my descendant is going to have to be a leaf. Or to be precise, actually, my descendant is going to have to be not necessarily a leaf, but it's got at most one other child. Okay? And for that reason, I have as many pointers as I need to connect as necessary. If I want to delete, let's go back to here. What am I going to do to, hold on, sorry. Uh-oh, now I'm in big trouble. Suppose I want to delete node 4. What am I going to do? I am going to delete the item. I'm going to delete. I'm going to overwrite me with my successor. I find my successor. It's got to have at least one, or at most one descendant. The case of deleting a node with one child is now something we already solved. So I'm going to overwrite my value with my successor and delete a node with at least most one child. That's the case that I've dealt with before. In both cases, I claim deletion can be done in time proportional to the height of the tree. Any questions about that? This is one to look at more carefully. So what is the good thing? The good thing is that all dictionary operations can be done in time proportional to the height of the tree. The best possible height of a tree with n nodes that I get is going to be log n, okay? Because if I want to have n nodes, the number of possible nodes I can have in my tree doubles with each successive layer. How many doublings does it take till I get n? Log n, okay? Now the trouble is that with these, I'm building this tree with insertion and deletion operations. The order of the insertions and deletions and what values go in there, that's not up to me, the tree. It's up to me, the guy that's calling the tree. And so I don't have any control of the order of the insertions. And depending, if I don't get any control of them, I could easily have my insertions be such that I keep inserting larger and larger. If I inserted them in sorted order, I would end up with a tree of height n that is a twig. Any questions about that? You don't get a choice when you're using a tree of what's the order of the insertion operations. Okay? So the height of a tree, as implemented the way that I've done, could be order n. Now, in fact, if I'm picking the guy that I'm going to insert randomly, I will expect that on average, the tree will be of height log n. Okay? This is something I will prove to you kind of why that's true when I analyze quicksort. The reason the log pops up here is the same reason why quicksort has an expected n log n sorting algorithm. But basically, if I'm picking my keys randomly, most of the time I'm going to get something more likely to get, I'm just as likely to get something in the middle as I am to get something at the ends. And to get something that's really bad, I've got to always get something at the end. It requires a great deal of unluckiness. But so if you guarantee me you're going to insert these items in random order, okay, that is this, I could count on my trees of being as height order log n, theta of log n. But unless I trust somebody really well, I don't believe it. That is why there exist more complicated dictionary data structures where they do on every insertion and a deletion, they take extra pain to balance the tree at the time of insertion or deletion. Okay? And you can't perfectly balance a tree on every insertion. Notice that if I had a tree here that was as beautifully balanced as it could, it had one slot for a new element. If I insert a 1 here, the only way to make this thing perfectly balanced binary search tree would rip up all the pointers. So I'm not going to maintain a height of exactly log n. I'm going to maintain a height of theta log n, maybe 2 times log n. And there are complicated ways, but intricate, but clever ways to ensure that whenever I rebalance it a little bit on every insertion or a deletion, so that the height is never going to be worse than twice log n. Okay, that's what a balanced binary search tree is. Hopefully in your data structures class, did they talk about red-black trees? Or AVL trees, or 2-3 trees? There's all kinds of beautiful trees, okay? where they do more work cleverly on each insertion to balance it, okay? If you can do the balancing in the right way, you can force the height to be log n, okay? And that then means that all of the operations we've talked about, insertions, deletions, and things like that, okay, will take order log n time. Any questions about it? So dictionaries are great because if we use a dictionary, the worst case of min, max, sort, min, max, insert, delete, predecessor, successor is always going to be log n. Okay, that's why we like balanced binary search trees. Often that explains where logs come from. And sometimes the log term comes from implicitly the idea that there's a log, a tree underlying it. If you think about doing a binary search on an array, when you search to the left, search to the right, implicitly there's kind of this tree idea where every node you'd have two possible divisions, and what's left is a recursion on a smaller set of things. Okay? Bottom line, all dictionary operations can be done in worst case n log n. And if you do that, then this is something you can assume as an elementary operation for designing better data structures, better algorithms. Any questions? If not, think about it, look at these things, and I will see you guys on Thursday.